All right. Now, here we are in Chapter 7, Section 7.1, and this is on the central limit theorem for sample means. Um, and so let me kind of tell you a little bit about where we're coming from, because where we're coming from is nearly identical to what we're going to be talking about in this chapter. Okay, there's just a slight twist, a slight change, but it's pretty much all the same idea. So let me kind of share with you what I mean by that. So previously here in chapter 6, all right, let's say we had our random variable S to stand for a sample. And let's say S represents the weight of black bears. And let's say that we had gone to a certain area and we trapped 30 black bears. So our data set would be composed of 30 weights from 30 black bears. So we might have one bear weighed 175 pounds, and another one weighed 181 pounds, and another one weighed 173 pounds, and so on. So we'd have 30 of those measurements. And then if we made a dot plot or a histogram, a dot plot would probably work better, but we could do a histogram as well, where we had 175 and 180 and 170, something like this. We would, put down like a dot for each one of these bears. So here, one bear was 175, another one was 181, another one was 173. And then we would just kind of keep putting dots down for the weight of each bear that was trapped. And what we would get is we would get a shape. And that shape is what we call the distribution of the data. So each datum in the distribution, so each datum in the distribution is the weight of a single bear. All right. And we could take the weights of 30 bears and we could find the mean weight, the average weight of those 30 bears. And let's say it came out to be, let's say the sample mean, so that'd be X bar, came out to be 176. All right. So we have a mean of this sample of 30 bears. Okay, that's kind of where we're coming from here in chapter 6. Now we're going to take this idea, just change it a little bit, and continue to build off of this idea. Okay, and that's what we're going to do here in chapter 7. So try and keep this idea in mind as I continue to describe what we're doing here in chapter 7 with the central limit theorem. So suppose that we have random variable x, where random variable x are the weights of all black bears in California, and that this lowercase x represents the weight of a single specific black bear in California. Then mu sub x is the mean weight of the entire black bear population in California. So remember, we use mu to represent a population mean. And sigma x is the standard deviation of the weight of the black bear population in California. And again, we used sigma to represent the standard deviation of a population. So previously, we determined the probability of finding a bear with a given weight. Now determine the probability of finding the mean bear weight given a sample size. So what I talked about earlier was taking one sample of 30 bears from the entire population and calculating a mean of that sample. But what if we took multiple samples of size 30? We didn't just take one, we took multiple samples, each sample of size 30. So sample one could have been 30 bears that were trapped in Yosemite. Sample two could have been 30 bears that were trapped in Northern California, maybe around Mount Shasta. And then maybe 30 bears which were trapped in Big Bear, California. Maybe 30 were trapped there. That would be our third sample. So we have multiple samples from multiple locations throughout the state. Now, from each of those samples, what if we calculated the sample mean? So here we've got the sample mean, which is the mean weight of 30 bears in sample one, maybe trapped near Mount Shasta. We have the sample mean from sample two, which is the mean weight of 30 bears in sample two, and that was maybe trapped near Lake Tahoe. And then we've got, X bar sub 3, which is the mean weight of 30 bears in sample 3, maybe trapped near Yosemite. So what we're starting to do is, instead of collecting a bunch of individual bear weights and seeing what shape they take, now we're collecting a bunch of sample means. And we're going to make a dot plot of all of these sample means from all of these samples that we're taking, and that is going to have a shape. We're going to have a distribution of sample means, not a distribution of bear weights like we did up here. We're going to have a distribution of mean weights. So if you take all of these sample means and you plot them, so there's sample mean 1. Let's see, here's sample mean 2 is missing, as well as 3. Here's 4. Oh, there's 3. There's 5, 6, 7. So, we start plotting all these sample means, and guess what? Those sample means are going to have a shape. They form their own distribution. And because they have their own shape, they have their own distribution, well, this distribution also has a center. And the center of that is the approximation of the population mean. So if we wanted to know what the average weight of all bears in California were, what we could do is we could go to different sites, different places in California, and trap a sample of 30 bears in each location. And then we could take the average weight of each group of 30 from each location, and we could graph. We could take all of those averages, and we can do an average of averages. We could take a mean of averages. And that would tell us what the population mean is for all of the bears in California. Because remember, one of the goals, one of the abilities of statistics is to infer the population at large from a smaller set of samples that you collect from the population. And so just like in chapter 6, when we had a normal distribution, the center of it okay, is a mean, and it also has spread. And that spread is a standard deviation. But notice here that we've got this subscript, which is x bar. So this means that we're looking at the average of the means. We're talking about the mean of the means. Okay, the mean of the means. And this is the standard deviation of the means. Okay, the standard deviation of this distribution here. And like I said, it turns out that when you calculate the mean of sample means, that it approximates the population mean. Now we call this distribution here, which is composed of sample means, we call that the sampling distribution of the mean. What kind of makes sense to me a little bit more is to call this the distribution of sample means. Distribution meaning the shape. So the shape of sample means. Okay. So this kind of from a 30,000 foot view, is what the sampling distribution of the mean means. Okay. How we define it. This is like the 30,000 foot view. If we get a little bit closer to ground level, okay, then we need to kind of go into this in a little bit more detail. So what's the definition for the sampling distribution of the mean? Well, this is how we can denote it, kind of like in a abbreviated form. So here we have our random variable, which is composed of sample means. It's normally distributed with a mean and a standard deviation. And we're going to go into some detail here about this standard deviation here in a minute. So this new random variable, capital X bar, is what we're referring to as the sampling distribution of the mean, and it consists of sample means. And like we mentioned before, the mean of the sampling distribution of the mean approximates our population mean. So the mean of our sampling distribution of the means approximates our population mean. Now, the standard deviation for the sampling distribution of the means is equal to the population standard deviation divided by the square root of n. So n here, sorry about that. N here refers to the sample size. So in the previous example, when I mentioned that we went to a location and we trapped 30 bears in each location, then the sample size would be 30. If we had gone to maybe 10 locations in the state of California, N would not have been 10. It's not the number of locations, it's how many we trapped in each location. And that's kind of what I explained here. The variable n is the sample size of each sample, which were averaged together. N is not the number of samples taken. So for example, if we'd gone to 15 locations in California and 30 black bears were trapped at each location, N would have been 30. It would not have been 15. Okay, so mu sub x bar represents the mean of the means of the weight of samples of black bears in California, and sigma sub x bar is the standard deviation of means of the weight of samples of black bears in California. Okay, so let's stop here with that. Let me know if you have any questions.